Have you ever felt like you're just drowning in data? I mean, we have more information at our fingertips than ever before, but making sense of it all, that's the real challenge. Today, we're going to dive into a really powerful mathematical tool that's designed to find the hidden simplicity in all that complexity. It's based on some brilliant work by Eunseong and Wolfgang Polonik. So here's our game plan. First, we'll look at the hidden shapes that are lurking inside our data. Then, we'll explore the cool smoothing technique used to actually find them. After that, we'll get into the mathematical breakthrough that makes all of this reliable, see how the theory holds up in the real world, and finally, we'll check out how this stuff is already shaping the future of data analysis.
All right, so the first big hurdle in modern data science is that we're dealing with these massive, high-dimensional data sets. Just try to picture it. Every single variable, every column in your spreadsheet is like a whole new direction, a new dimension. Yeah, it gets complicated really fast.
Now, here's a thought to get us started, and it's a little provocative. On the surface, most of the data we collect, well, it's lying to us.
But here's the thing. It's not that the data points themselves are wrong. No, the lie is in the complexity we think we see. We look at it and see this chaotic, high-dimensional cloud of points, but the real story, the actual structure, is often way, way simpler.
And this brings us to a really crucial idea in machine learning. It's called the manifold hypothesis. And it's this amazing concept that suggests our messy, high-dimensional data isn't just scattered around randomly. Instead, it actually follows the path of a hidden, much simpler geometric shape, something called a manifold.
Think about it like this. Imagine you have thousands of cities scattered across a globe. The ambient dimension would be like trying to describe their locations using these super complex 3D coordinates starting from the center of the Earth. It's confusing, right? But the intrinsic dimension is so much simpler. It's just the latitude and longitude on the 2D surface of the globe. That's the hidden map. And finding that map, well, that's the key.
Okay, so if our data points are just these scattered dots, how in the world do we reveal the hidden map they're sitting on? Well, this is where a really powerful statistical method comes into play.
The technique is called kernel smoothing. And really, at its heart, it's just a very clever way of making an educated guess about that underlying surface by looking at the data points we can actually see.
Let me give you an analogy. Imagine you want to estimate the temperature at an exact spot on a map. You wouldn't just use the single closest weather station, would you? Of course not. You'd look at several stations nearby, and you'd probably give more weight or more importance to the ones that are closer. Kernel smoothing does exactly that, but for data. It picks a point, looks at its neighbors, applies a special weighting rule based on distance, and then calculates a weighted average. And that process, repeated over and over, smooths out our picture of that hidden surface.
Now, for a long time, trying to apply this technique to these complex, hidden manifolds was, well, it was tricky. It was almost like a black art. Different problems needed different custom-built approaches, and you could never be totally sure if your method was truly reliable. That is, until the breakthrough work by Bay and Polonik.
And right here, in their own words, you can see the core of what they did. They established a unified point of view. See, before this, data scientists were kind of like craftspeople, building these custom tools for every single task, and just hoping the next one would work. What Bay and Polonik did is they didn't just invent another custom tool. They built the entire industrial-grade, guaranteed-to-work toolkit for pretty much any job involving smoothing on manifolds.
So what's in this powerful toolkit? First off, it gives us mathematical guarantees. This means we can reliably estimate not just values on the hidden surface, but properties of the surface itself, like its slope or its curve. Second, and this is absolutely crucial for anyone working with real-world data, it gives us something called finite sample bounds. This basically tells you exactly how much you can trust your results, even when you only have a messy, limited set of data, not some perfect infinite data set. And finally, it establishes asymptotic normality. This is the hardcore proof that your model isn't just a lucky guess. It guarantees that as you feed it more and more data, your estimates will predictably and reliably get closer and closer to the actual truth. It's what turns a clever trick into robust science.
Okay, so mathematical proofs are one thing, but, seeing is believing. So the authors actually ran simulations to show these guarantees in action. And this slide just illustrates it perfectly.
Look at the left. With only 500 data points, the estimate, that's the gray bars, it's a little rough, right? A bit all over the place. But now look at the right. With 10,000 data points, look at how perfectly the estimate fits that theoretical red curve. This is asymptotic normality playing out right in front of us. The more data you give it, the closer to the truth it gets. This is theory meeting reality. It's awesome.
So, we've established the math is solid. The simulations prove that it works, but where does this actually make a difference out there, in the real world? Well, the applications are where this research really starts to shine.
This toolkit is actually the engine behind some incredibly useful techniques. Kernel density estimation uses it to find clusters or hotspots in data. Kernel regression uses it to make way more accurate predictions because it understands the data's underlying shape. And then there are concepts like the heat kernel signature, which use it to analyze and compare complex 3D shapes. Like, for example, telling a computer that a donut and a coffee mug have a similar underlying structure. And that is absolutely critical in fields from computer graphics all the way to medical imaging.
So really, the big idea to take away from all this is simple. In an age where we are just overwhelmed by complexity, the most powerful breakthroughs often come from developing the tools to find that elegant simplicity that's hidden just beneath the surface.
What Bay and Polonik have given us is a more reliable map and a much better compass. And it really makes you wonder, our data's just filled with all these undiscovered landscapes. What kind of secrets are we going to find now that we have the right tools to map them all?